Welcome to 18.1, which is entitled Refraction. We're going to learn what refraction is, how do you calculate how far light refracts when it enters into a substance, and something what's called total internal reflection. And you see this picture of a rainbow here, which kind of represents all of those pieces right there. I did a quick Google search for refraction. Maybe you're familiar with refraction, but light bending as it enters some sort of optically dense medium. Here's a picture of trying to aim at a fish. It looks as though it was here, but if you throw at it, you're going to miss high. So because of the refraction of the light coming from the fish into your eyes, the classic straw in the glass demo, you've maybe seen this before. The Pink Floyd album. You can click on photography here. Here's some pictures that maybe you've seen before. Droplets of water. A person's head. But refraction. The refraction is the bending of light because of light is actually slowing down. The speed of light, we all know, is 299,798,458, 299,792,458. And when it enters into some other medium, such as this glass here, or plastic, or water, it actually slows down. So when it's coming in at an angle, it bends inward as it slows down. And likewise, if it was coming out of it, it speeds up and then bends away. The first person to quantize this, his name was Wilbur van Rooyenschnel, and he came up with a law that dictates how to figure out how far light bends when it enters into water. And his law is N1, which N1 stands for the index of refraction of whatever the medium is that you're in currently, sine theta 1. Theta 1 is the incident angle. And remember, it's always with respect to the normal. N2 is the index of refraction of what you're going into, and theta 2 is the refracted angle. Not the reflected angle, but the refracted angle. I've got an interactive demo here that kind of shows you how this works. Up here, I made the top an air, and I made the bottom water. And so I can move this around and show you. And this does Snell's law for you. It does all the calculations. And I can change it into something that's more optically dense because water has an index of refraction of 1.33. I can make it into glass. Certain kinds of glass have different indexes of refraction. This one has an index of 1.52. I can make it diamond, which is 2.42. So the more optically dense you'll see, the farther that the light refracts into it. And if it was the same, if I made it air on the top and air on the bottom, there would be no bending of light. So it just enters in. Now going the other way. Here's my going from glass. Let's make it water. Going the other way. You can see that this, anytime we go into it, it always bends towards the normal. Now going out is a little bit different. As I bring this out, you'll see that the refracted angle gets bigger and bigger until this refracted angle goes right along the surface. We actually call this the critical angle. This is a critical angle. It's critical when you're trying to get out of something more dense. What ends up happening, this is called total internal reflection. It doesn't break through the medium, it just skips off it and bounces internally. And this critical angle, so if your incident angle, this angle right now, if my incident angle is bigger than that critical angle, then I have total internal reflection. If my incident angle here is less than the critical angle, I have refraction. So this critical angle is something that deals with total internal reflection. Now you'll notice too, as I make this more and more dense, it's going to bend further and further. And now I have total internal reflection, which is actually what makes diamonds sparkle so much. The fact that the light bounces around, it comes in the top and ends up going back out the top is what gives it that sparkling effect. Now, the index of refraction, there are numbers for all sorts of optical this website these are the numbers of index of refraction for just about anything you can think of. You just scroll down through here, and it gives you the optical density. So these are sorted by the least index to the most down here, silicon. So now, example problem. A light beam in air hits a smooth lake at an angle of 30 degrees. At what angle is it refracted? I'm going to take it over to my notebook. So you're going to use Snell's law. And you're going, it's going into, so the index of refraction for air is 1.00 times the sine of my angle of incidence, which is 30 degrees. Ooh, careful. It looks like the picture's labeled that this is 30 degrees, so that means that this is 60 degrees. We're going into water. So, pull out my calculator, and we'll take 1 times the sine of 60. I want to make sure that I'm in the degree mode, and I am. So, the sine of 60. And I'm going to divide by 1.33. And then I'm going to take the inverse sine of that. And I get 40.6, or 40 degrees. So, theta 2 is 40 degrees. So this angle, and that makes sense if you look at the picture. If this is 60, that means that this looks like it could make sense. So 40 degrees. And that's using Snell's law to kind of figure out how far do things bend when they enter into some other optical media. There's a bunch more example problems here that we'll probably do in class, or I'll have you do on your own or something like that. But it's basically just using Snell's law. It talks about, let's see here, there's crown glass. There's a bunch of things that you can just look up. The diamond, 2.44. All these things have indexes of refraction which can be looked up, and I believe that they're in your notes. What the index of refraction actually is, it's a ratio of how much light slows down. Like you remember for water, the index of refraction ended up being 1.33. The speed of light is 3 e to the 8th. So this is the speed of light in water. You can figure that out. So you just take 3 e to the 8th divided by my index of refraction, and that will tell me how fast light will go in that medium. So instead of being 3 e to the 8th, it's 2.3 e to the 8th. So it slows down a little bit. And we saw before total internal reflection. Total internal reflection is when this critical angle, when your incident ray here, when that gets too big, you get total internal reflection. So, and we spoke about it before. I'll just talk about it one more time. So this angle right around here, here's my critical angle. If I get larger than this, I get total internal reflection. If it gets smaller than that, I get refraction. Now you'll notice it only happens when I'm going from a more dense medium like water into a less dense medium like there. Like if I go this way, if I go from air into water, it doesn't matter what. I can put this thing anywhere and it will always go into water. It will always go into glass. It will always go into diamond, but it won't always come out of it. You'll notice that something that like diamond, their critical angle is much, much smaller than that of air. Here's the critical angle for our diamond. Now what's unique about the critical angle is that if this is theta 1, that means that the theta 2 is 90 degrees. So if here's my critical theta 1, this is supposed to be going right along the surface here, so this is going to be 90 degrees. So when you're finding critical angles, here's the secret. To finding the critical angle, you use 90 degrees. So going back over here, the critical angle, some applications of it when you see it in real life. Mirages. Mirages are an example of total internal reflection. The ground, as you heat it up, it heats up the air, and then the air has a larger index of refraction, and you can see it actually makes like a perfect line. Some of you guys have seen, you'll see them in the summertime, that as the light goes from it, it hits the ground, and then there's this critical angle. Here it reflects at you, and here it refracts down into the pavement, and it's absorbed or reflected specularly. So you guys have probably seen mirages. You'll look for them in the summertime. You'll see them. Fiber optic cable. Maybe you've seen some of these Christmas trees and a lot of our internet these days. You hear a lot about Google Fiber. That's a way to send data through a glass. It's almost like a wire, but it's a glass strand, a fiber. And what's neat about a fiber is that you can send all sorts of colors. You can send a red light, you can send green down here, you can send blue, and they all carry a different message. And at the very end, you put a prism which separates out the red, the green, and the blue, and that way you can get different streams of data all on the same fiber. Not just one stream like a copper wire. Diamonds. Light comes in, totally internally reflects. You'll see off the bottom down here, these two facets. Light refracts, comes in, refracts, totally internally reflects, and then refracts back out, giving them that sparkle. This is a website called LifeGem. If you'd like, you can turn yourself into a diamond. You send them a certain amount of you. You can do it with hair. You can just take, I think a regular haircut would make like 10 diamonds. So, or you can do it with your pets. It's pretty crazy, but ranges in price from about $2,000 to $25,000, depending upon the size and color of the diamond you want to have made out of your person or pet. And then finally, an example problem. Find the critical angle for diamond. And we're going to do that, and we're going to call it a day. Find the critical angle for diamond. So let's draw a diamond here. And we've got a ray hitting the surface, and then it goes along the side, because that's what the critical angle actually is. We're looking for this critical angle, but we know that this is 90 degrees. So we're just going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1, you're going from the diamond, and if you remember, it was 2.42. Times the sine of theta 1, which is unknown. We don't know that. That's the critical angle. We're trying to go into air. And theta 2 is 90 degrees. Now, believe it or not, 1 times the sine of 90 is just 1. So to find my actual critical angle, I'll pull out my calculator, and I'll take 1 divided by 2.42. And then I will take the inverse sine of that, 24.4. So the critical angle, 24.4 degrees. And just for kicks, I wonder if this works. I go over here to diamond, and if you look at my angle right here, around 24.2. I didn't do a good job. I could get it a little bit bigger, and that would hit my right along the surface. So yeah, this actually works pretty well.